Hi again, everybody. This is the second lecture in the series of 3 lectures on the moving frames and invariants for submanifolds in parabolic homogeneous spaces. So today I will speak about curves. So this is why in the title you see curves instead of submanifolds. And today I will be giving probably more examples and will be less naive. So I recall that during the first lecture, we went through some basic definitions of what is the symbol of an arbitrary submanifold. We revise this definition today. We'll discuss what are the flat curves or model curves for us, and then discuss what kind of canonical moving frame we can expect to get. Plus, we'll check a few examples and end up with the generalizations. But today there will be no submanifolds of dimension 2 and higher, just curves. In particular, this is well aligned with the notion of distinguished curves, and I will cover this at the end of the talk. So I will also mention how the theory of curves works not just in homogeneous cases, but in curved parabolic geometries. But very briefly. So that's the plan for today. And let's start moving. So let's recall what we had last time. So we were dealing with an arbitrary parabolic homogeneous space. And for those who wants to have some examples, they may think about flag varieties of flags or symplectic flags if needed, orthogonal flags. But I will speak in the language of general semi-simple Lie algebras and parabolic subalgebras, and there were groups and subgroups. In particular, the most important example for me would be, of course, projective space. But I will also speak about G2 examples. I will give a few examples. And I recall that we have this filtration on our manifold, and so we would want to study curves on such manifold. And by curve, I always mean non-parameterized curves, so essentially one-dimensional submanifolds. And of course, a very first invariant, a numeric invariant or integral invariant would be the smallest subspace in my filtration, which contains tangent lines to my curve. So essentially, for each of this, what is the smallest subspace in this filtration for which our curve is an integral curve? And I'm not going to limit myself to just curves tangent to t-1 fam. And I recall that if we now have an arbitrary curve, and for curves I use this letter gamma all the time, so gamma would denote a curve. So I recall what was the definition of a symbol. So for symbol, we just were taking tangent line to our curve. Well, we were moving it to the origin, and taking its graded associated subspace. So what will end up would be just a one-dimensional graded subspace living in some G minus K for some K greater than 0. And here K is exactly this minimal positive number, such that gamma is an integral curve of T minus Km. But because we take a graded subspace associated to the tangent line, we kill all the tails, so we are left only with a homogeneous part of this tangent line. So essentially, it's just an element in G minus K. And I recall that the symbol is defined modulo the action of G0. So the symbol for us today will be a homogeneous element X in G minus, which is viewed under the action of the group G0 and the non-zero scale. So M and X, like, and is just a one-dimensional subspace spanned by a homogeneous element in G minus. And often I will, so in previous lecture, I often use the letter N to denote the symbol. Today, for me, the symbol will be the same as this element X. So very often I will speak about the prolongation of X instead of prolongation of N. They will be essentially interchangeable during this lecture. So any questions at that moment, because I'm repeating what I had last time, but that's really very important, that today a very basic starting point for me will be just a homogeneous element in G minus, homogeneous element of degree minus K. And it will serve as a model for tangent space of our curves. It will be used to approximate tangent spaces. Okay, so last time I was saying that the only assumption in the whole theory is an assumption of a constant symbol. Here, in case of curves, this becomes even weaker because we have a very nice property that G0, the group G0, acts on lines in G minus K. So essentially, projective space associated with G minus K with a finite number of orbits. This is true for complex and real numbers. So this would work for complex homogeneous spaces, complex parabolic homogeneous spaces as well as real ones. So essentially we have only a finite number of possible symbols for curves, and finite number means that we can assume that the symbol is constant on an open subset. Just because we have no continuous parameters on the level of symbols. So therefore, in case of curves, we always can assume that we have a constant symbol if we, of course, remove singularities. We might have singularities in our curves where the symbol changes just at the point. So next was the definition of prolongation, and the prolongation was used to recover the maximal possible symmetry algebra for curves, well, submanifolds with a given symbol. It is literally, well, it works exactly as before in this case. So the only simplification is that when we compute the prolongation, yeah, so this first line actually is much easier now. So all negative part consists of this one-dimensional subspace X. So this could be even further simplified because this is only the space sitting in negative, so one-dimensional subspace. And that will sit in G minus K. And then we keep on constructing the prolongation via this recurrent formula, and each time we just take a bracket with X itself, because X is the only element in N in the symbol. So at each step, our next so elements of degree I in our prolongation are those elements which bracket with X and end up with what we had at degree I minus 1. So it's very easy exercise to really compute such prolongations. And as we had before, we know that this symmetry, so as before, I just copied literally the theorem we had before, So the maximal possible symmetry of, well, gamma instead of n would be more correct here, is exactly the dimension of such prolongation. And the flat curves for us will be orbits of the one parameter subgroups, xptx. So these are our flat or model curves, and we would try to approximate any other curve with this symbol by these flat curves. So again, a very straightforward transition from what we had last time. And the questions become the questions remain the same. So we would want to fixing such element X and G. We would want to understand if we can we construct some nice moving frame along our curve of type X or with symbol X, and how many invariants do we have, and in which degrees they happen to be. So this, and when I say invariants, I always mean fundamental invariants, the ones which control if our curve is flat or not. So that is a reminder of what we had last time with minor modifications for the case of curves. Okay, well, so let's move forward. Here's another very interesting phenomenon that exists only for curves. So it is known that for each x of degree minus k, we can always find elements h of degree 0 and y of degree k such that they form a basis of SL2 subalgebra. This result, again, is due to Morozov and Winberg, essentially. I think Winberg for complex numbers, Morozov in characteristic 0. Just by looking at the definition, we know that this SL2 subalgebra or SL2 triple, how they often called, would belong to our prolongation. Again, it's straightforward to see that H would belong to 0 degree elements in prolongation, just because XH is proportional to H, is 2x, sorry, or well. And so H belongs to degree 0 elements of the prolongation, and then clearly Y belongs to degree K of the prolongation, because X bracketed with Y happens to be in prolongation of degree 0. So we always have this SL2 sitting inside prolongation and acting actually effectively on our curve. So we can use this SL2 triple or SL2 to take a shortcut and compute a prolongation much faster. Because what we know is that so prolongation itself contains this SL2, so this is an SL2 module. On the other hand, G is SL2 module itself, so prolongation is glued from some irreducible submodules that appear in the adjoint action of SL2 on G itself. And again, by definition, since X is the only element of negative degree in the prolongation, we can easily prove that this prolongation is actually this SL2 plus all SL2 submodules, which are concentrated in non-negative degree. So this gives us also a very simple way to compute prolongation starting from this SL2 triple. Just decompose G into the sum of reducible submodules, and since everything is graded, these reducible submodules will also be assumed to be graded, and then check which of them do not contain any negative elements of negative degree. And further on, the subgroup that corresponds to XHY, so acts transitively, actually not on the orbit of XPTX itself, but on the closure of this orbit. So you may think about this XPTX as an affine line in the projective space, while the complete action of SL2 would complete a affine line to the complete to projective line. So this is why we need to take a closure. And thus, any flat curve or any model curve essentially is always a rational curve or its cover. So it's always so in complex numbers. If you think about complex numbers, this is essentially always P1. And over reals, of course, we should think about projective lines or curves or their covers. But, well, I mean, locally the structure is always like on the projective line. So this is sometimes called we often say that such curves always possess a projective parameter. Moreover, it can be proven that such projective parameter is does not depend on the choice of the SSL2 triple. So if you choose a different one, we'll get an equivalent projective parameter on our curve. So all curves are very nice. All model curves, sorry, not all curves, but all model curves or flat curves in our case are very nice. And again, this is a phenomenon of dealing with parabolic homogeneous spaces, because we rely here very much on G being semi-simple. So the first items, the theorems of this Morozov and Winberg would not work in general. Let's now see how it all works. So we'd like to move to construct a canonical moving frame. So let us recall what is a moving frame and how this would work in case of curves. So we fix any curve with a symbol x. So we, as of now, we fix a certain element x of degree g minus k, and would want to get a canonical moving frame for each curve. So as before, I call that what is in general moving frame is just all elements in G that feed over curve gamma in this canonical principal P bundle. So we have standard principal P bundle, and then we just pull it back, well, reduce it to the curve gamma in G by P. And as before, we have a left invariant Cartan form omega, and this is our main instrument for constructing moving frames for curves, as well as actually for submanifolds. But in case of submanifolds, the theory becomes a bit more complicated. So we normally would denote by pi or by pi minus 1 the restriction of the projection to Q minus 1. So a moving frame is any subbundle essentially, but we would want not just an arbitrary subbundle, but certain canonical subbundle. So, and I recall that we construct a normal moving frame by imposing conditions on values of omega on our subbundle. So we look at how what kind of subspaces we can get if we apply omega to our subbundle, and we impose linear. So that's very important that all our conditions would be linear restrictions on this space. So, and I recall the example we had for projective curves. For projective curves, we were able to find a canonical moving frame such that omega would belong to this 4-dimensional subspace in 8-dimensional Lie algebra SL3. And I recall that out of these 4 forms, 3 of them correspond to the symmetry algebra of the flat curve, which is conic in this case. So our flat curves would be conics in this situation. While the only extra form, omega O2, measures the difference of how far our curve is from a conic and defines what we call fundamental invariance for a curve. And last time we were computing this all in detail, so I'm not going to spend much time on this example. I'd rather want to move forward to other examples. So Now let us see, so as I say, we would want to impose some linear conditions on the image of omega on our moving frame bundle, canonical moving frame bundle. So these restrictions or conditions are called normalization conditions. And so what we would want to have as a normalization condition is a subspace W in G that satisfies the following three conditions. So first of all, it is concentrated in non-negative degree. That's one thing. Second, it is complementary to both the prolongation. So in each degree, in each non-negative degree I, so I is any non-negative degree, I want Wi to be complementary to the prolongation of x in degree I and the bracket of x with gi plus k, sorry, so it's not I plus 1, it's I plus k here. So essentially prolongation of x and image of add x fitting in degree I. So this is a subspace which I'm able to absorb in some way. And I absorb prolongation because I keep the prolongation Lie algebra inside the frame, my normalization conditions as I'm doing in case of SL of curves in P2. So I keep a subspace that corresponds to the prolongation untouched. Plus, I'm able to normalize all, or absorb all parts that belong to the image of add x. The rest is the choice normalization choice. This is what will be left. And I want this normalization choice to be invariant with respect to the non-negative part of my prolongation. Again, the first two conditions, of course, are just open conditions. You can always select such graded subspace W. The third one is an invariancy condition, and as I'll show later, does not always exist. But let's suppose for now that it exists. Yeah, so this such W may not always exist. However, there is a very nice situation where it always exists. This is a case where our prolongation of x is reductive, meaning it's a sum of semi-simple Lie algebra and possibly some center sitting in degree 0. So if this prolongation is reductive, then we can play an interesting trick. We can first of all take an orthogonal complement with respect to the killing form of G. So we can take an orthogonal complement with respect to the killing form of G, and then take its non-negative degree. So this is a subspace. Orthogonal complement, non-negative part of the orthogonal complement. But then I know that this subspace will be complementary to the prolongation of x, but it would still be too large to be complementary to the image of add x. So I'm reducing it further by saying that I'm looking only for the elements in such orthogonal complement that is killed by y, where y, I recall, is a part of cell2 triple x hy that always exists for my x. So it's a nice trick, algebraic trick, and it is possible to prove that such subspace would satisfy all three conditions. Naturally satisfies the first one because I take only non-negative degree in the orthogonal complement. It is complementary to the prolongation of x because I take it as a part of orthogonal complement to the prolongation of x. And this thing ensures that it lies in the, it is complementary to the image of add x. And again, to understand why it happens, we can think about the decomposition of G into the sum of reducible SL2 modules. And each such action of x would preserve such module. And in each such submodule, the elements killed by Y would be exactly those which are complementary to the image of X. That's just how a cell 2 acts on reducible modules. This is a trick we will use often in our examples, and to be honest, this trick does work here as well in the cell 2 in this trivial example, because in this simplest example we have X to be lower trigonal, like X corresponds to omega 1 0, H corresponds to omega 0 0, Y element corresponds to omega 0 1, and then we can check that this slot first of all lies in the orthogonal complement to the SL3. It is positive, and it is killed by the action of Y, the bracket of Y, because essentially it's just Y squared sitting here. So, this trick we see here will also play an important role further on when we will discuss the case of more general case of submanifolds, and it resembles a little bit the harmonic algebraic equivalent of harmonic analysis that is used when we deal with normalization conditions for curved parabolic geometries in general. So it's much easier here. So having such normalization conditions, we can ensure that we do have a canonical moving frame. And this moving frame is characterized by this very simple condition. So it is just the set, we can prove that there is a canonical moving frame E over gamma, such that the image of omega on this bundle lies inside the prolongation of X plus our normalization conditions. And I recall that if we were able to put our frame inside the prolongation of X itself, our curve would be flat. But this W is like what brings us this additional invariants that control how far we are from our model flat curve. So now, and we can reformulate this in a more precise manner. So we can, I'll outline the proof a little bit on the next slide. But suppose we believe we can construct such moving frame, then we can decompose omega as omega 1 plus omega 2, where omega 1 takes values in prolongation of X, and omega 2 takes values in this W in our normalization conditions. So what happens then? Omega 1 is just flat projective connection on gamma, nothing else. Well, it is possible to show that omega 1 is a proper Cartan connection on gamma, first of all. Well, but probably we have some non-effectiveness part in our prolongation. So there might be some ideal that doesn't act on the curve itself. So actually only SL2 triple will be effectively acting on our curve. The rest, like the sum of all SL2 submodules in non-negative degree, would not act at all. But still, it could be, of course, we can ignore or we can question by this like non-effectiveness ideal. But we'll be left with, anyway, with just a flat projective connection. And it defines a canonical projective parameter on gamma. So not that, assuming we do have this normalization conditions, invariant normalization conditions, we get a canonical projective parameter not on model curves, but actually on any curve. So it is clear that if you think about conics in P2, then of course we know that conics in projective plane are nothing but embeddings of P1, so they do have a nice projective parameter, but it is less trivial or less obvious to understand that any curve on which is non-degenerate, meaning it is not reduced to a line, would also carry a very natural, projective parameter. Well, this is what we get out of this normalization conditions. Well, the second part, omega-2, would be an equivariant form on our Cartan connection, so to say, a projective connection, and it defines us complete system of fundamental invariants. And in particular, gamma is locally flat, and if only if this sitting in W is identically zero. So in a way, I can say that the complete geometry of curves in parabolic homogeneous spaces is governed by SL2 triples. As soon as we have a SL2 triple, of course, SL2 triples, graded SL2 triples, which agree with the grading. So for each graded semi-simple algebra, we may describe all graded SL2 triples. Then each such SL2 triple would define as a type of curves. And this SL2 triple would also define the prolongation. And if this prolongation happens to be nice, then occasionally we will have, or often we will have, normalization conditions. And again, we can understand how many fundamental invariants in which degrees we have, because essentially it is all governed by all these spaces. So they are complementary here. So if we know how large is this space, we know how large is W, so we know Wi, so we know how many invariants in degree I plus something, I mean, because we might use some tricks of going from one parabolic homogeneous space to lifting curves from parabolic homogeneous space to a bigger, or to correspondence parabolic homogeneous space, and normalizing them there. And I recall we discussed this last time by looking at how to lift curves from projective plane to curves on three-dimensional or first jet space over projective plane, but it's just a flag variety of the group SL3. Well, brief overview of the proof. I'm not going to deep detail, but I just give you an idea that it's been developed quite some time ago by me and Igor Zelenko in the case of curves. That at that time it didn't work at all for higher dimension. And the idea is, as I say, so starting with Q-1, which is a P bundle, start to reduce it to a series of principal bundles, QK or gamma. So each of them is a principal bundle with a reduced structure group. So it's smaller and smaller. And to control it, so to have an understanding how large would be of our structure group at each stage, this is the Lie algebra that corresponds to the structure group. So at each step, we take first prolongation of X up to degree K, including degree K, and then we take all elements from G of degree higher than K. So this Lie algebra is becoming smaller and smaller, and it descends to a non-negative part of the prolongation when K becomes like infinitely large. But luckily, we don't need infinite number of steps because we are inside the finite dimensional Lie algebras. So this is how far we are able to reduce structure groups. And at each step, again, we kind of guessed what happens at each step. We define QK as a set of all such points in QK-1, such that the image of our omega restricted to QK-1 takes values in what we need in the prolongation of X plus W, modulo all elements of degree K and higher. And again, we can prove that at each step, this condition nicely reduces qk minus 1 to qk with a reduced structure group, which has this structure Lie algebra. And essentially, at a finite number of steps, at the depths of our that is the depth of our semi-simple algebra, will reach the canonical moving frame. So I'm now switching to examples. So any questions so far? Okay, so let's see how it works in practice. So it was like very simple so far and very straightforward. And most, all examples in a way are governed by what I said. So we will be checking different SL2 triples inside different semi-simple algebras, and we'll check what happens with curves of that type, and which SL2 triples correspond to which curves. Very standard example, that is the generalization of the example we had before last time, is the generalization of the example of integral curves of curves in P2. So suppose we have an arbitrary non-degenerate curve in Pn, and non-degeneracy means that it doesn't belong to any linear subspace of smaller dimension. Then we can play the trick of lifting the curve, and in this case, this trick essentially says that we can consider right away the oscillating flag of our curve at each point. So, and this gives us a lift from a non-degenerate curve in Pn to a curve in flag variety. And such curves we get will always have a symbol that belongs to, is of degree -1, so it will be tangent to t minus 1. So the distribution on the flag variety of degrees, that corresponds to elements of degree -1. Then again, from non-degeneracy and this prolongation procedure, we can show that the corresponding curve type or symbol is given by this element. So it's ones sitting under the diagonal. And the prolongation will be exactly xhy SL2, so it will be not bigger than this SL2 triple. This SL2 is just an irreducible embedding of SL2 inside SL n plus 1. And again, a very simple computation shows that our normalization condition W can be chosen as the subspace spanned by powers of y, starting from y squared. So, and from this, we know that any such curve will have exactly n-1 fundamental invariant, and they will sit in degrees, well, actually 3, 4, and up to n plus 1. If we think about the curve in the flag variety. But if you think about the curve in Pns, then we need to have how many derivatives? Probably n-1 derivative before we lift it here. So if in terms of curves in Pn, this will be invariance of degree n plus 3 through to n plus 1, something like that. This is exactly the case where we have our prolongation to be exactly SL2, and SL2 is of course reductive. So the streak plays the streak with orthogonal complement, and then looking at element filled by y plays very nicely. And again, it's very easy to check that of course these elements are killed by through y because they commute with y. And this is exactly the algebraic picture that stays behind so-called Belchinski invariance, but I'm not going to go into the details here. So it governs how can we compute not just differential invariance of curves in PN, but also invariance of linear differential equations. Well, similarly, some other examples. So if you look at curves in conformal spaces, then again, it's easy to check that we will have only one type of curves if we restrict ourselves, of course, to the positive definite conformal spaces, then all one-dimensional subspaces in the tangent space will be equivalent under the action of G0, which will be just an action of SON on Rn. And each of such one-dimensional subspaces would correspond to conformal circles as flat curves, so we can compute the prolongation, which will be again irreducible. No, it will be actually not. But well, I'm not going to. I didn't think about just one of the examples where we can use conformal circles to as approximation of any curves in the sun. And other cases where the same trick works, generic curves of generic type. Then again, generic type means these are the curves that do not belong to any subspaces of smaller dimension. So it's curves in n-dimensional Grassmannian in R2n, isotropic Grassmannian in dimension n, and isotropic n-dimensional subspaces in R2n, where R2n can be viewed both under the action of Sp2n or SONn. In all these cases, we have the theory that works very nicely where prolongation of X is reductive. And actually, more general case, which corresponds to linear systems of R ODEs of order n-1. These are n-dimensional subspaces in R of dimension, well, Kn would be Rn, for any R greater than or equal to 12. This is a generalization of the example I see here. I showed here for the case n equal to 1. And this was worked out actually in works of Siashi at the end of 80s. So I will come to G2 examples where I'll play a little bit in more detail how it works. But first, what happens if you have no invariant normalization conditions, and do such examples exist? And to my knowledge, the smallest example where such case exists is this one. So it's two-dimensional. So it's a Grassmannian of two-dimensional subspaces in R5. And in such case, we can, if you have a generic curve here, you can take its escalating flag, and it will be subspaces of dimension 2, then 4, and then 5. So, and then it turns out that if you analyze the symbol and the prolongation of the symbol, then it can be proven that in such case there are no invariant normalization conditions. And the computation was done very explicitly in our paper with the result, the link back to 2019 or 13. So what happens in such cases? So we can still define a normal moving frame as we defined before, but it will, as if we would have no invariancy, then it will no longer be a principal fiber bundle. So we will, omega-1 will not define in general Cartan connection, and we will have no uniformly defined projective parameterization, for example. But we would still have for example, the proof that prolongation of X is the maximal possible CDL. Because we would still be able to have an absolute parallelism on this reduced normal moving frame bound. So yeah, and more generally, very nice, interesting thing. So if you look at, so what is actually this two-dimensional subspaces in R5? It's the same as ruled surfaces in P4 if you take projectivization, because each two-dimensional subspace becomes a line. A curve of lines will be ruled surface. So when we speak about curves in Grassmann variety GR25, then we essentially speak about ruled surfaces. If you look at how it works, so ruled surface, there is a nice theory of ruled surfaces in even dimensional, in odd dimensional projective spaces, like in P3, for example. But there is no such nice theory for ruled surfaces in even dimensional projective spaces. So it's an interesting observation. And okay, let's now come back to the G2 examples we had last time and play a little bit with them. So I recall what we had before, and we'll be discussing contact parabolic geometry. So I leave 2, 3, 5 geometry as an exercise. And here G-1 is 4-dimensional, and it can be identified with cubic binary forms under the action of G0, which is GL2 in this case. And I recall that we have one generic non-contact curve type, so curves which do not belong to contact distribution, and 3 types of contact curves depending on the multiplicity of roots. Well, tangent line will sit in this S3R2 will be essentially cubic polynomial or cubic binary form, and depending on the multiplicity of roots, we'll have 3 different cases like triple root, double root, and the single roots. And this is what we did last time, and I will bring back the pictures in a second. I'm going to play with normalization conditions. So for non-contact curves, our symmetry algebra was reductive, actually, SL2 plus SL2, and the cubic binary. And we do have, actually, in all these cases, we have invariant normalization conditions. I'll just list through. These are kind of computations we had last time. So for triple root, I told that we can have a nice natural lift to G2 by Borel to the Borel geometry, so to say, for G2. So G by P12, normally Borel is denoted as P12. So for double root and the single root, we had a 5-dimensional non-reductive symmetry algebra as a prolongation, but yet normalization conditions do exist, as we shall see in a second. And no multiple roots, that's also an interesting thing. So in triple root and no multiple roots, in both cases, the prolongation is just SL2, but these are 2 different SL2s, and they have different decomposition of a joint representation. And because of this, in this case, triple root, we have 1 fundamental invariant sitting in a very high degree. And here in no multiple roots, we have 3 fundamental invariants, but appearing much earlier. And let's probably now switch to a picture I was drawing last time and play a little bit with that. Just a second, I'll share the pictures I had last time. So you should see now the images we played around last time. And let's probably start with this one. So is it all clearly seen on the screen?
Yes, yes.
Okay, so should be able to. Yeah, I need. Actually, I did the thing. I'm sorry, I probably need to open it in Paint. Just a second. I'll stop sharing. I'll reopen the same image in Paint, and we'll make some drawings. Yeah, that's it. Yeah, so let's look at this. So let's recall what we have. So this is a G2 with a contact grading. So this is a grading given here from -2 to -1, 0, 1, 2. And our symbol here is n, which is one-dimensional. So this is what I denoted by x last time. Let's make it folder. So this is x. This is what I call x. So essentially, this element is x. So clearly, we have y sitting here and h sitting somewhere here as a one-dimensional subspace in Cartan subalgebra. And we've seen last time, the prolongation is complete Cartan subalgebra, two-dimensional. And then these two families of orthogonal roots, short and long, so the prolongation is a cell 2 times a cell 2. So this is our prolongation. And we would want now to understand what is our normalization conditions. Normalization condition has to sit in non-negative degree, meaning it should sit somewhere here, somewhere in this part. So I'll change the color, life more interesting. So our normalization condition should be somewhere here. Next, what we know, it should be complementary to prolongation of n, and it should be, so if you want it to be invariant, since a prolongation of n, or positive part, non-negative part, or zero part of prolongation of n contains Cartan subalgebra, so automatically invariance with respect to Cartan subalgebra would mean that W should be the sum of some root spaces. So, and now if you look at how X acts and what is an image of X, so it is clear to see that these elements would belong to the image of X, and they will still be negative. But those ones will exactly be the ones which do not belong. First of all, they do not belong to the image of X. They are complementary to the image of X. They sit in positive degree, and they are complementary to non-negative part of prolongation of X. Moreover, we immediately see that it is invariant with respect to this non-negative part, because what is the non-negative part here is just a cell 2 sitting in 0 degree and y, and an element y sitting in degree +2. So this SL2 that is spanned by short roots clearly preserves this elements of degree +1, and of course y just commutes with all these elements. And in fact, we can check that the same trick, so I explained before, taking an orthogonal complement to the prolongation and checking which elements are killed by y is exactly the one I have here. Those elements will be exactly sitting in the orthogonal complement and are killed by y. The orthogonal complement will be all roots which are not marked by red, and those will be the ones which are, those blue ones will be the ones which are not killed by which are killed by y. So as a result, we have this W as a normalization condition, this 4-dimensional subspace. And with respect to the action of GL2 sitting inside prolongation of n, we see that it is an irreducible representation. So in a way, we can say that our fundamental invariant is a cubic binary form. And it sits in degree 1 in terms of Lie algebra, because we need to take one more derivative when we go from the curve to the Maurer-Cartan form over this curve. This means that essentially this will be invariance of degree differential degree 2. And all curves which are flat of our type, this type, will be defined by a system of 4 second-order ODEs. So this is what we get immediately just looking at this GL2 picture. So let's probably see what we have further on. For the triple roots, I recall we had a way to prolong them to G2 by P12 geometry, and I will skip this example for a second. Probably will return to this later. So this is an interesting one, yet another one. This is a case where we had a double root and a single root, and I marked red our prolongation again. So this is our prolongation of X. This is a cell 2 plus one more element sitting in the Cartan subalgebra and one more root subspace, which will be exactly this R2 two-dimensional solvable the algebra. So let's again play the same trick and see what we can get. This is a non-reductive case. So this is a case where we do not have an orthogonal complement. So that's our X, our Y here. But I can show that we can still find this nice invariant normalization condition. So how does this work? So we know it should sit again here in the non-negative degree. So it should sit here. It should be complementary to elements of to red dots, essentially, to the root spaces corresponding to the Cartan subalgebra and the root spaces that belong to prolongation. So we are left with 1, 2, 3, 4, 5 root subspaces, and we have to choose only among root subspaces if we want to have invariance with respect to prolongation, 0 elements inside prolongation. Because again, it contains Cartan subalgebra. So the only other condition we have to check that it is complementary to the image of X. So what do we have as an image of X? We clearly have this thing sitting in the image of X. I just put it like that. And this thing, because X essentially moves this lowest root into these two roots. And also, we do not want this one because it's also in the image of X, because it moves this other root. All others, on the other hand, will not lie in the image of X, and they will give me exactly what we need. So these two blue dots would give me a W that again will be, it's easy to see that it will be invariant with respect to the non-negative part of prolongation of X. And again, we guarantee that it is invariant with 0 part of prolongation of X because we've chosen them among the sum of root subspaces. So we just need to check that it is invariant with respect to the bracket with this Y, but that's again kind of obvious. But also we have to check that it is invariant with respect to the bracket with this other element, which I can denote, for example, Y prime. And again, you see that Y prime takes one blue dot to another blue dot, but in general leaves the subspace invariant. And it also gives us a hint how further normalization. So we do get, so in general, we got 2 fundamental invariants here, but we also have an understanding how further reductions might work if we have non-zero fundamental invariants. For example, if we know that if this fundamental invariant corresponding to this dot is non-zero, then it can be used to normalize this one. So normally, if we would want to proceed and construct absolute invariants, not just fundamental invariants, then we would need to do further branching and decide whether this invariant is 0 or not 0, and whether we can kill this one or not. So there will be 2 cases where both invariants vanish, where one invariant vanish, and then automatically the other one can be killed, or when this first one vanishes, the other doesn't vanish. 2 other cases we have here. So when we have here one case where we can lift everything to G2 by P12, and then I probably mentioned last time that in this case the prolongation will be exactly a SL2. And this SL2 will be a principal SL2 in G2, meaning its adjoint representation will be reducible 11-dimensional representation. So we would know that the image of X acts like is 10-dimensional inside this 11-dimensional representation or complement. And then we'll have only one fundamental invariant. On the other hand, if you look at this generic case of contact curves, then this is another SL2 triple that shows up here, and its adjoint representation. It's again some computation with the SL2 triples inside G2. It has a different adjoint representation that splits into, I think, irreducible representations of dimensions 3, 3, and 5. And each of them gives us exactly one fundamental invariant. In each of them, we have exactly one-dimensional subspace killed by Y. So this is about how it works. So I just have this dimension of W here is 3, and the dimension of W here is 1. So only one fundamental invariant, but in a very high degree. Very high, well, I have to compute, I think it's 7 or 8. I have to compute this more accurately. Here it's much smaller degree, but 3 fundamental invariants. So again, I think the purpose of this was just to give you an idea how, in general, this works. So return the lecture. How it's the complete understanding of curves in parabolic homogeneous geometries actually is governed by SL2 triples. And to the extent that one can come up with very combinatorial way of describing number of invariants and their differential orders by just looking at I don't know, by just looking at degree of X and eigenvalues of H. These two combinatorial invariants will be sufficient. But so far this has not been done, so it's an interesting probably project for a student who wants to learn how SL2 triples happen how to classify SL2 triples inside semi-simple algebras, or graded semi-simple algebras. Yeah, so a few generalizations and discussions, and this will be probably the last slide. So first of all, what happens if we are in a curved parabolic geometry, not in a flat one? And if you go back to the proofs of our moving frame construction, you'll see that there are no conditions at all on what equations omega should satisfy. So in particular, of course, omega, like a Maurer-Cartan conformal on a Lie group does satisfy the equation d omega plus omega omega equal to 0, while on the curved parabolic geometries, d omega plus omega omega is just a curvature tensor. But nowhere in the proofs and in the definitions we used that d omega plus omega omega might be 0 or non-zero. So in case of curves, actually, the complete theory works for any curved parabolic geometries. So we have the same types of curves, and it is by definition well adapted to the notion of development of curves. So we can reformulate all the results and all the canonical moving frame constructions for and the notion of a symbol, etc., for curves in arbitrary parabolic curved parabolic geometries. And then, of course, instead of model curves or flat curves, you would have exactly the notion of distinguished curves. But then we would have also all other curves, which we would be approximating by distinguished curves. So that's one good thing. And again, this is something unique for curves. It does not generalize that easily for submanifolds. Yes, so what happens if you start thinking about submanifolds, and this is kind of a preview of the lecture I will have next time. So next time I will speak about general submanifolds. So a lot will stay. So we will still use a notion of normalization conditions, but just as a preview, we would need to split these two sequences, and this cosmology will show up. We would need to split these two exact sequences in an invariant manner. And our normalization conditions will be exactly the splittings, and then I will be showing you how similar argument can be used to construct canonical moving frames for arbitrary submanifolds. And probably you recognize here that when I speak about something that is complementary to the image of X, that's exactly the image of this map, when n is just spanned by one element X. But again, we will speak about these exact sequences and splittings and normalization conditions and what kind of cosmology we get next time. Yes, so that's been the end of the talk.
Thank you very much.
Thank you. So, questions? Also simple.
Maybe I would like to ask you a question about a case which you indicated when you have a non-reductive complement.
Non-reductive.
Yeah.
Yep.
So you said you have two fundamental invariants.
Yep.
Do they have different weights?
Well, yes, absolutely. And yeah, I'll probably share the screen back. So this is the case. Yes, they will be, one of them will be in degree 2, another in degree 3. But again, if the one in degree 2 is non-zero, then the other one in degree 3 can be killed by reducing further the structure. So
you cannot just subtract one from the other, right?
Yes, yes, exactly. This action acts as a subtraction from one. Exactly. So this is what happens. So if we want to map this picture to like your work on differential invariants of curves of this type, one needs an extra reduction probably. So the conditions, but on the other hand, if you just think about flatness conditions, there is simply no other choice. There will be two conditions, one of degree 2 and the other in degree 3. So all curves, all flat curves of this type would be defined by two differential equations, one of degree 2, another of degree 3. Plus, in addition, the condition that our curve is contact and has a double root, which would be two first-order equations.
How do you see this orders 2 and 3 from this picture?
So this element sits in degree +1 in the Lie algebra. This one sits in degree 2 in the contact grading. Yeah. I need one more derivative to compute Cartan form of a curve. Yeah. To just compute the image of the Cartan form.
Okay, yeah.
So I think, and again, I have to be careful. So when I speak about degrees, I speak about weighted degrees. So I need 2 or 3 derivatives if I take derivatives only along contact directions. Maybe this translates into different degrees if you just take trivial filtration, so to speak. So I treat the degree in the direction outside of contact distribution as a derivative of degree 2.
Yeah, yeah.
To be precise.
It's weighted, yes, yeah.
Yeah.
Boris, maybe you like to ask a question. Can we just go through an example again of how you determine the order of your invariants, the jet order of your invariants?
Yeah. So again, just disclaimer. So we speak about weighted jet order.
That's fine. Yeah.
So there are two games to be played when we compute the order of invariance. So first of all, we have to understand whether we use a trick of prolongation, of lifting, or no, to be precise, of lifting the curves to corresponding spaces. Like if we take a curve in projective space and lift it to the curve of flag varieties, we have to take a number of derivatives.
Yeah.
So we have to compute how many derivatives we take during this prolongation step or lifting step, or probably lifting step. Like here in case of a triple root, we need to take one derivative to lift our curve to the from G2 by P2 to G2 by P12. So this is one ingredient. The other one is just the degree of the image of the Cartan form. But we have to understand that when we compute the degree of the image of Cartan form, we take a derivative by itself. And well, and again, this numerics, yeah, might be. I have to be more careful here. Probably, I may revise this in a more rigorous manner, because I've seen these questions asked many times. So I wanted to give a hint how those degrees can be computed. But as I have never done, I have never written down this carefully. There might be some inaccuracies, to be precise. So, but in general, the degree is governed by these two procedures. One of them is by these two ingredients. One of them is lifts of curves to corresponding spaces. Another one, the degrees of W. Nothing else. Well, essentially, we have no other data, so this should define as a complete data. Anything else?
No, thank you.
No? Thank you very much.